Welcome! Today, we'll explore LeetCode problem number 1644, lowest common ancestor of a binary tree 2. This problem focuses on finding the lowest common ancestor of two nodes in a binary tree. We'll discuss the problem, break it down into manageable steps, and explore an efficient solution. Let's get started. In this problem, we are tasked with finding the lowest common ancestor, or LCA, of two given nodes, P and Q, in a binary tree. The lowest common ancestor is defined as the lowest node in the tree that has both P and Q as its descendants. A key detail here is that a node can also be considered a descendant of itself. However, this problem introduces an additional challenge. Unlike the standard LCA problem, one or both of the nodes P and Q may not exist in the tree at all. If either node is missing, the correct output is null. We'll be working with a binary tree represented by the root node, where P and Q are tree node objects, and our goal is to return either the LCA node or null based on the conditions. Let's look at an example to understand this better. Here we have a binary tree represented as follows. The root node is 3, with two child nodes 5 and 1. Node 5 has children 6 and 2, while node 2 further has children 7 and 4. On the other side, node 1 has children 0 and 8. In this example, our goal is to find the lowest common ancestor of nodes 5 and 1. These nodes are clearly part of the tree, and their LCA should be the lowest node where both are descendants. The output for this example is 3. This is because 5 and 1 exist in the tree, and the lowest common ancestor of these two nodes is the root node, 3. This node is the deepest node in the tree where both 5 and 1 are descendants. Now, let's consider another example to explore a different scenario. Here, we are working with the same tree structure, but this time the nodes of interest are 5 and 4. Node 5 is the parent of node 4, which means 5 is an ancestor of 4. In such cases, the lowest common ancestor is the ancestor node that is closest to the descendant. Therefore, the output here is 5. Since 5 is itself an ancestor of 4, it is the lowest common ancestor in this case. Now, let's take a look at another example where one of the nodes does not exist in the tree. The tree structure remains the same, but the nodes we are checking are 5 and 10. While node 5 exists in the tree, node 10 does not. In this problem, when one or both nodes are missing from the tree, the output must be null. This ensures that the algorithm handles invalid nodes appropriately and only returns an LCA when both nodes are present in the tree. In this example, the output is null because, although node 5 is present, node 10 is not part of the tree. This highlights the importance of checking for the existence of both nodes before attempting to find their LCA. Let's also consider some additional constraints and edge cases to ensure our solution is robust for all scenarios. There are a few specific edge cases to consider. First, if the tree is empty, meaning root is null, the output must be null regardless of the values of P and Q. Next, if either P or Q is not found in the tree, the result should also be null. Additionally, even though the problem guarantees that P and Q are different, the solution should still account for the possibility of errors where P and Q are mistakenly the same. Finally, if the tree contains only one node, the output depends on whether P and Q match that node. If they do, return that single node, otherwise, return null. These edge cases ensure that the solution handles all possible inputs correctly. To solve the problem of finding the lowest common ancestor, or LCA, of two nodes in a binary tree, we need to address a unique challenge. One or both of the nodes, P and Q, may not exist in the tree. This requires us to carefully validate their presence as part of our solution. One straightforward method we could consider is the brute force approach, which involves tracking the paths from the root to both nodes. Here's how it works. We traverse the tree twice, performing two separate depth-first searches to locate the paths to P and Q. Once we have these paths, we compare them to find the deepest common node. While this method operates within O(n) time complexity, as it requires two tree traversals and O(h) space complexity for the recursion stack, it has a major drawback. It doesn't account for the case where one or both nodes are absent from the tree. A more robust alternative, the optimized recursive approach, tackles the problem in a single traversal. This method not only finds the LCA but also verifies whether P and Q actually exist in the tree, making it a more comprehensive solution. In the optimized recursive approach, we use a depth-first search where each recursive call returns critical information to its parent node. Specifically, it tells whether P or Q has been found in the current subtree. When both nodes are located beneath the same subtree, the current node becomes the LCA. This approach is highly efficient, as it requires only a single traversal of the tree, achieving a time complexity of O(n). The space complexity remains O(h), where h is the height of the tree, due to the recursion stack. One of the key advantages of this strategy is its ability to handle the edge case where one or both nodes are missing. By propagating information about the presence of P and Q up the recursion stack, we ensure that the solution remains valid even in these scenarios. Additionally, this method is more efficient than the brute force approach, as it avoids redundant work, and its recursive nature lends itself to cleaner, simpler code. For these reasons, the optimized recursive approach is the chosen strategy for this problem. The key insight that makes the optimized recursive approach so effective is realizing that we can solve the LCA problem in a single tree traversal by propagating information about the presence of P and Q. Using a helper function, we can simultaneously determine the LCA, if it exists, and verify whether P and Q are present in the tree. This dual-purpose approach ensures we meet all constraints of the problem efficiently. Now, comparing the trade-offs between approaches, the brute force method may be simpler in concept, but it fails to handle edge cases and performs unnecessary work by traversing the tree multiple times. On the other hand, while an iterative solution might be possible, it introduces significant complexity due to the need for parent tracking and handling edge cases manually. This makes the recursive approach the most practical and robust choice for this problem. By leveraging its ability to validate node presence while finding the LCA, we achieve a solution that is both efficient and reliable. To solve the problem lowest common ancestor of a binary tree 2, our goal is to find the lowest common ancestor, or LCA, of two nodes, P and Q, in a binary tree. The LCA is defined as the lowest node in the tree where both P and Q are descendants. Importantly, a node can also be considered a descendant of itself. However, this problem introduces additional complexity, either or both nodes may not exist in the tree. If one or both are missing, we must return none. To tackle this, we break the solution into clear steps. First, we need to ensure we fully understand the LCA definition. Next, we validate whether both P and Q are present in the tree. Finally, we implement a recursive helper function to traverse the tree and identify the LCA. Let's start by walking through these steps. The LCA is determined by traversing the tree and finding the lowest node where both nodes exist as descendants. Before we can confidently return the LCA, though, we need to confirm that both nodes are actually present in the tree. This validation step is crucial for handling edge cases where one or both nodes are missing. To achieve this, we'll use a helper function to traverse the tree and check for the presence of P and Q. Once validation is complete, we move on to the recursive logic to identify the LCA itself. The recursive helper function is central to finding the LCA. Here's how it works. If the current subtree is empty, the function returns none. If the current node matches either P or Q, it returns that node, signaling that one of the target nodes has been found. The function then recursively searches both the left and right subtrees. If both subtrees return none values, this indicates that the current node is the LCA, as it is the lowest point where both P and Q are found. Otherwise, the function propagates the none result upward, which essentially means it continues searching in the direction where one of the nodes exists. After the recursive traversal, we use the results from our validation step to ensure both P and Q were actually found in the tree. If either node is missing, we return none. Otherwise, we return the result from the helper function. The insights here are significant. The recursive traversal ensures that every path in the tree is explored while simultaneously searching for P and Q. The separate validation of node existence ensures correctness, especially in edge cases. Additionally, the algorithm is efficient. Each node in the tree is visited only once, resulting in a time complexity of O(n), where n is the number of nodes in the tree. The recursive process relies on the call stack to manage intermediate results during traversal. This makes the recursive approach particularly well suited for binary trees, as the structure of the tree naturally aligns with a divide and conquer strategy. To implement the complete algorithm, we start by defining a function to validate whether a given node exists in the tree. This function uses recursion to check if the target node matches the current node or if it exists in either the left or right subtree. Next, we define the main LCA function. Within this function, we set up the recursive helper function. The helper function checks if the current node is none, returning none if that's the case, or if the current node matches P or Q, returning the current node as a result. It then recursively explores both left and right subtrees. If both left and right return non-none values, the current node is identified as the LCA, and this result propagates upward. Otherwise, the function returns the non-none result from its left or right subtree, effectively continuing the search. Once the helper function is in place, we validate the existence of both P and Q by using the node_exists function. This ensures that our algorithm doesn't incorrectly return a result when one or both nodes are missing. If either P or Q is found to be absent, the function immediately returns none. Otherwise, it calls the helper function, starting the recursive LCA search from the root of the tree. Several edge cases are handled by this approach. For instance, if the tree is empty, the algorithm returns none right away. Similarly, if P or Q is missing, the validation step ensures the algorithm doesn't proceed unnecessarily. Another edge case occurs when P is a direct ancestor of Q or vice versa. In such scenarios, the algorithm correctly identifies the ancestor node as the LCA. The recursive helper function ensures efficiency by propagating results upward and discarding irrelevant branches. This avoids redundant computations, contributing to the overall efficiency of the solution. The time complexity remains O(n), as each node is visited once during the validation and once during the LCA search. The space complexity of the algorithm is O(h), where h is the height of the tree. This is because the recursive calls use the call stack, and the maximum depth of recursion corresponds to the height of the tree. This makes the algorithm memory efficient for balanced trees, where the height is proportional to the logarithm of the number of nodes. However, for highly unbalanced trees, the space complexity could approach O(n). Overall, this algorithm is both elegant and robust. By separately validating the existence of P and Q, it ensures correctness, even in edge cases. The recursive approach is intuitive for binary trees, leveraging their structure to simplify the search for the LCA. This combination of correctness, efficiency, and simplicity makes the solution an excellent choice for this problem. Here, we start by defining the lowest common ancestor method within the solution class. The goal of this function is to find the lowest common ancestor of two nodes, P and Q, in a binary tree. To achieve this, we first define a helper function called find. This function is used to check if a given target node exists in the tree. It recursively searches through the left and right subtrees, returning true if the target node matches the current node or is found in either subtree. If the current node is null, it returns false, indicating the target is not in this branch. Next, we define another helper function, LCA_helper, which actually computes the lowest common ancestor. If the current node is null or matches one of the nodes P or Q, it returns the current node as a possible ancestor. Otherwise, it recursively checks both left and right subtrees for potential ancestors. If both left and right subtrees return non-null values, it means the current node is the lowest common ancestor, as the two nodes are found in separate subtrees. If only one subtree returns a non-null value, it propagates that result upward. Finally, before proceeding to calculate the LCA, we first verify that both P and Q exist in the tree using the find function. If either node is not found, the function will return none. If both nodes P and Q are confirmed to exist in the tree, we proceed to call the LCA_helper function, starting with the root of the tree, to identify and return the lowest common ancestor. This ensures that the function operates only when both nodes are present, avoiding incorrect results. The LCA_helper function will recursively traverse the tree, leveraging the logic we discussed earlier, and ultimately return the node that satisfies the conditions of being the lowest common ancestor. This implementation ensures clarity and correctness by breaking the problem into smaller, reusable helper functions, and by validating the inputs before attempting the computation. Here, we begin by defining the main method lowest common ancestor, which takes in the root of the binary tree in the two nodes, P and Q, whose lowest common ancestor we want to find. The first step is to ensure that both P and Q actually exist in the tree. To do this, we use a helper method called findNode. If either P or Q is not found, the function immediately returns null. This ensures that we don't proceed with invalid inputs. Next, if both nodes are present, we call another helper function, findLCA, which performs the actual logic to determine the lowest common ancestor. Let's take a closer look at the helper methods. First, the findNode method uses recursion to traverse the tree. It checks whether the current node matches the target node, returning true if it does. Otherwise, it continues searching in both the left and right subtrees. This method ensures we can verify the presence of any node in the binary tree. Finally, we start defining the findLCA function, which is responsible for the core logic of finding the lowest common ancestor. If the current node is null, we simply return null as there's no ancestor to be found at that point. Now, in the findLCA method, if the current node matches either P or Q, we return the current node since one of the nodes we are looking for is itself an ancestor. Next, we recursively call findLCA on both the left and right subtrees to explore further. The key logic comes after these recursive calls. If both the left and right recursive calls return non-null values, it means that P and Q are found in different subtrees of the current node, making the current node their lowest common ancestor. In this case, we return the current node. On the other hand, if only one of the recursive calls is non-null, it means both P and Q are located in the same subtree. In such cases, we return the non-null result. Finally, we include the definition for the treenode class, which represents the structure of a node in the binary tree. Each tree node has a value, and pointers to its left and right children, both of which are initially null. This completes the implementation of the solution in Java. In this first example, both nodes, P and Q, exist in the tree. We are working with the binary tree shown, where P is node 5 and Q is node 1. The first step is to verify that both nodes are actually present in the tree. To do this, we call the find function starting at the root. For P, we begin at the root node 3. We traverse into the left subtree and find node 5, confirming that P exists. The function returns true for P. Next, we repeat the process for Q, node 1. This time, we start at the root again and traverse into the right subtree, where we locate node 1. The function returns true for Q. Since both nodes exist, we can move forward to finding their lowest common ancestor. To find the lowest common ancestor, we call the helper function LCA_helper starting at the root node 3. First, we explore the left subtree, where node 5 matches P. This means the left subtree returns node 5. Then, we explore the right subtree, where node 1 matches Q. This means the right subtree returns node 1. Now, since both the left and right subtrees return non-null nodes, the current root, node 3, is their lowest common ancestor. The final output for this example is node 3 as the LCA. Moving on, let's consider a scenario where one of the nodes does not exist in the tree. Here, P is node 5, but Q is node 10, which is not present in the tree. In this second example, we begin by verifying the existence of P and Q. For P, we call the find function starting at the root node 3. We traverse into the left subtree, where we locate node 5 and confirm that P exists. The function returns true for P. However, for Q, node 10, we again start at the root and traverse through the entire tree, but node 10 is not found. The function returns false for Q. Since Q does not exist in the tree, there's no need to proceed with finding the LCA. The function immediately returns none as the result. Therefore, the final output for this example is none. Now let's consider another special case where both P and Q are the same node. In this last example, both P and Q are the same node, which is node 5. Again, the first step is to verify their existence. We call the find function starting at the root node 3 and traverse into the left subtree, where we locate node 5. The function confirms that P exists and returns true. Since Q is also node 5, the process is identical, and the function also returns true for Q. With both nodes verified, we proceed to find the lowest common ancestor. We call LCA_helper starting at the root. As we traverse into the left subtree, we reach node 5, which matches P and also matches Q. Since we've found one of the nodes directly, it becomes the LCA. The final output for this example is node 5 as the LCA. In this problem, the time complexity is determined by two main operations. First, we need to check if the nodes P and Q exist in the tree. This is done using the find function, which performs a depth-first traversal of the binary tree. In the worst-case scenario, the function might visit all n nodes in the tree, making its time complexity O(n). Since we execute find twice, once for P and once for Q, the total contribution from this part is O(n) plus O(n), which simplifies to O(n). Next, we move to the part where we actually find the lowest common ancestor, or LCA. For this, the LCA_helper function is used, which also employs a depth-first traversal of the tree. Similarly, in the worst case, this function could visit all n nodes, making its time complexity O(n) as well. Now, when we combine these two parts, the total time complexity of the solution becomes the sum of O(n) for the find function and O(n) for the LCA_helper function. This gives us O(n) plus O(n) equals O(2n), which simplifies to O(n). Shifting to space complexity, this is determined by the recursion stack used in both the find and LCA_helper functions. For the find function, which performs a depth-first search, the maximum recursion depth corresponds to the height of the binary tree. If the tree is balanced, the height is O log n, but if the tree is skewed, the height can be as large as O(n). Similarly, the LCA_helper function also performs a depth-first traversal, and its recursion depth is likewise proportional to the tree height. In the best case, this is O log n, while in the worst case, it is O(n). Since the recursion stack is reused sequentially, meaning that the find and LCA_helper functions are not running at the same time, the total space complexity is determined by the larger of the two recursion depths. Therefore, in the best case, the space complexity is O log n, and in the worst case, it is O(n). Comparing this solution to a naive approach, the brute force method might involve storing all paths from the root to P and Q in separate lists and then comparing those paths to find the first common node. While this naive approach also has a time complexity of O(n), it would require additional space of O(n) to store the paths, which makes it less space efficient. By contrast, the current optimized solution avoids storing paths explicitly and instead uses recursive traversal, reducing the space complexity to O(h), where h is the height of the tree. To summarize, the time complexity for this solution is O(n) in all cases, while the space complexity ranges from O log n in the best case to O(n) in the worst case. This makes the solution not only time efficient but also more space efficient compared to the naive approach. When working on this problem, there are several common mistakes to watch out for. First, one major issue is not handling cases where one or both of the nodes, P or Q, are missing from the tree. If you assume both nodes are always present, your solution might incorrectly return a result. Instead, you should traverse the tree while keeping track of whether P and Q are found, ensuring your output is valid. Another common mistake is misunderstanding the recursion base case. This happens when your base condition doesn't account for null nodes or the cases where the current node matches P or Q. By skipping these checks, your recursion might behave incorrectly and return the wrong ancestor. To fix this, always use a base case like if root is none or root equals P or root equals Q to handle these scenarios properly. Finally, some solutions return the first match without fully exploring both subtrees. This is problematic because P and Q might be located in opposite subtrees, and failing to check both would lead to incorrect results. The solution here is to ensure you explore both subtrees completely and combine their results to determine the lowest common ancestor. Another issue to consider is overlooking edge cases, like when P and Q are the same node. In this situation, the lowest common ancestor should simply be the node itself. Without explicitly handling this scenario, you might introduce unnecessary recursion or even return an incorrect result. To fix this, include a condition to immediately return P or Q if they are the same. Additionally, inefficient duplicate traversals can significantly impact performance. For example, some approaches traverse the tree multiple times, once to check for the existence of P and Q separately, and then again to find the LCA. This increases the time complexity unnecessarily, potentially up to O(n)². Instead, you can optimize your solution by using a single traversal to both locate the nodes and determine the LCA simultaneously. This approach not only saves time but also simplifies your implementation. Now, let's focus on some key insights that can help during interviews. First, understanding binary tree traversal techniques, such as in-order, pre-order, and post-order traversal, is essential. Many LCA problems, including this one, rely on recursive post-order traversal. You should approach the problem using the divide and conquer strategy over the tree structure, breaking down the problem at each node. To handle cases where nodes may be missing, use helper variables to track whether P and Q are found during recursion. This ensures you only return the LCA when both nodes exist in the tree. If either node is missing, return null as specified in the problem. For optimization, aim to combine the existence check with the recursive search for the LCA. This eliminates redundant tree traversals and improves the overall efficiency of your solution. There are also related problems that can help you strengthen your understanding of LCA patterns. For instance, LeetCode 236, the lowest common ancestor of a binary tree, assumes both nodes always exist, so it's a simpler variation of this problem. LeetCode 235, which focuses on the lowest common ancestor of a binary search tree, leverages the unique properties of BSTs to optimize the solution. Another variation is LeetCode 1123, where the goal is to find the LCA of the deepest leaves in the tree. This requires a similar recursive approach but with added considerations for depth. Finally, LeetCode 543, diameter of a binary tree, introduces tree traversal techniques that are useful for solving LCA problems. Exploring these related problems can help you recognize patterns and refine your approach to tree-related questions. When solving this problem, there are multiple approaches you can take, each with its own trade-offs. The most common is the recursive approach using post-order traversal. Here, you traverse the tree recursively and return the current node if it matches P or Q. By combining the results from the left and right subtrees, you can determine the LCA. This method has a time complexity of O, n, and a space complexity of O, h, where h is the height of the tree, but it depends on the recursion depth. Alternatively, you can use an iterative approach with parent pointers. This involves storing parent-child relationships in a dictionary and traversing upwards to find the LCA. While this avoids recursion, it requires additional memory for the parent pointers, leading to O, n, space complexity. Finally, a hybrid approach combines recursive traversal with flags to track the existence of both nodes. This efficiently handles missing nodes in a single traversal, offering a good balance between simplicity and performance. Each method has its strengths, so choose the one that best fits the problem requirements and constraints. Great job! We've covered LeetCode problem number 1644 and explored how to find the lowest common ancestor in a binary tree. Remember the key points: efficient tree traversal, handling edge cases, and understanding LCA applications. Thanks for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!